let's talk about reaction mechanisms, which is our last big topic of this chapter. So, while balanced equations tell us the relative proportion of reactants used and products formed in a reaction, they normally do not give detailed information on the actual molecular steps that occur during a reaction. Sometimes they do, just essentially by luck, just by random chance they do. But most of the time, the reaction is more complicated than just the balanced chemical equation. The thing that does give us information on the detailed step-by-step process of the reaction is what we call a reaction mechanism. The reaction mechanism tells us the step-by-step process that needs to occur, each individual collision between molecules that needs to occur for a reaction to happen. So, most chemical reactions are made of more than one of what we call an elementary step. Now, there are some reactions that do take just one elementary step, but most take more than one. Now, each of these elementary steps is really just a collision. We call it an elementary step because it can't be broken down any further. It's the simplest interaction that can take place, which is really by definition a collision, two things bumping into each other. So we have three different molecularities that can happen for these elementary steps. We can have a unimolecular elementary step, which is involving just a single molecule. We can have bimolecular elementary steps, where you have two molecules participating, and then very, very rarely, three molecules could collide to have an elementary step occur. Now, these termolecular processes are exceedingly rare. They do happen. It has been proven, at least as best as we can prove, that there is such a thing as a termolecular elementary step where you do actually have three different molecules coming together with just the right orientation at the same time with the correct amount of energy for a process to occur. But it is so incredibly rare that if you turn in a scientific paper and claim to have found a termolecular process, people will just laugh you out of the journal. They'll say, no, you didn't. Go back, do more research. It takes a whole lot of convincing to convince people that you found a termolecular process. For our purposes, we are just going to ignore termolecular processes from this point forward. Again, they do exist, they're out there, but they are so rare that we're just going to pretend like they don't exist. Now, a few of you might have noticed that when I was talking about elementary steps up here, I said that an elementary step is essentially a collision. It's the simplest interaction that can take place. But then down here I said we can have unimolecular processes, where we have just a single molecule. How does a single molecule have a collision? Well, it's not a trick statement. I'm not lying. These unimolecular elementary steps are actually collisions, but the tricky thing, well, it's not actually a trick, the kind of tricky thing about it is that they are colliding, they're just not colliding with something that they're reacting with. So even if you have just one molecule that is maybe breaking apart into two things, this is what we call a decomposition reaction, even if we have that occurring, there is always going to be something that instigates the reaction, that starts the reaction going. And that is usually either the molecule bumping into another molecule. Again, that second molecule is not actually participating in the reaction, so it's not counted as part of the molecularity, but it essentially is kind of giving it the nudge to make it go. Or it could be colliding with maybe the walls of the container that it's in, something like that. So it's still colliding with something. It's just not colliding with something that's participating in the reaction. So it's not actually a lie to say that this is a collision. It's just not colliding with some something that's participating. So if we do happen to have a chemical reaction that occurs in a single elementary step, then what I said several videos ago about not being able to take the balanced chemical equation and write the rate law, that actually does not apply. If you have a single step process, then you can actually just take the balanced chemical equation, take the reactants, and plug them into the rate law, and that will give you the rate. And that's what you see here with these three. Again, we're going to ignore those, pretend like they don't exist. So if you have a single step process where you just have one thing, it bumps into the walls of the container, and it forms some products, then the rate law is just going to be that one reactant with everything else in there too. You always have to have the rate and K. But as far as the actual concentrations, it is just the one reactant. If you have a bimolecular process, and that is the only step in the whole reaction, then your rate law would be this. You would have second order. So you have the rate is equal to K times A to the second. And if you have another bimolecular, but it's two different molecules, then it's just K times A times B. So if you have just one step, and again, this is only true if the whole process occurs in one step. If you have a single elementary step process, you can in fact just take the reactants and plug them in to the rate law. So, why can't we use this for all reactions then? Well, the short and sweet answer is that most reactions occur in multiple steps. There are quite a few. There's it's not rare by any means. There are quite a few that do happen in one step, but most reactions occur in multiple steps. It's not just you go from reactants to products and you're done. You go from reactants to intermediate and then to products, or maybe to intermediate and then to another intermediate and then to products. Most chemical reactions have at least 2 steps, and it is not unusual at all to have 3 or 4 or even more steps, just depending on the reaction. But it is very common to have at least 2 steps. And so because we have multiple steps, we can't just take the balanced chemical equation and create the rate law. All right. Real quick here before we move on to looking at the analogy. Intermediates, we're going to bump into these more later on, but intermediates are kind of like transition states in that they are high energy forms of the molecules. Intermediates are not very stable. However, they are isolatable or isolable. Brain's not working, but what the word should be. You are able to isolate it. We'll say it that way. You are able to isolate an intermediate. So if you remember from the last video, I said that you will never have a jar of transition state molecules. You could actually have a jar of intermediates, because you have to have some amount of energy to get out of this well here. Intermediates are at the bottom of an energy well, unlike transition states, they're at the top of an energy hill, essentially. So you could actually isolate an intermediate, but you would have to keep it probably very cold. Most intermediates are not terribly stable. They really want to be on one side or the other. And so while you can isolate it, it's not the easiest thing to isolate, and it's not the easiest thing to keep. It tends to break down fairly quickly. Right, so moving on here. Let's think about these multi-step processes and why we can't just take the balanced chemical equation and write the rate law. So we're going to think about this in terms of cars moving on a highway. So if we have two different toll plazas on a highway, we have Toll Plaza A and Toll Plaza B, and we have someone stationed over here in this 3 section area here. And this person, in both of these situations here, they are keeping track of how many cars pass them per minute. So they're tracking essentially the rate of cars, how many cars go past them every minute. Now, if they're keeping track of that, what they're going to see is they're really going to be figuring out how quickly the cars are getting through the toll plazas. So they're not really tracking how quickly the cars can move. They're really tracking how quickly the cars get through each of these toll plazas. But even more specifically than that, what they're actually measuring, when they measure how many cars go past them per minute over here, what they're actually measuring is how quickly the cars go through the slowest toll plaza. The slow toll plaza is going to limit how many cars go past over here. So if, for example, in this first one here, and make sure I'm not getting ahead of myself. No. So if you look at the first example here, Toll Plaza A is the slower one. And we know this because the cars are piling up behind Toll Plaza A, and they're not piling up behind Toll Plaza B. Essentially, as fast as the cars can get to Toll Plaza B, they get cleared through, and they keep going. If Toll Plaza B was slower than A, they would start to pile up here, which is actually what we see down here in the second possibility. But in this first one here, because Toll Plaza A is slower and the cars are getting bunched up, waiting to get through this toll plaza, that is really what the guy is measuring over here. When you're measuring the number of cars that come through over here, you actually don't know how quickly cars could get through Toll Plaza B. All you know is that they go through at least as fast as they get through A. So what we're really measuring, again, is the slowest step. The slowest step determines the overall rate. And so the same thing is true this second possibility here, where now Toll Plaza A is the faster one. So the cars are getting through A fairly quickly, but then they're bunching up on Toll Plaza B because they're not getting through very quickly. And so the person that's down here watching the cars come by and counting them really has no idea what the rate is for Toll Plaza A, because they can't really see. They don't know how many cars are going through Toll Plaza A. They just know the rate for this second step. And so this is really important for figuring out what's going on with chemical reactions. The reason why, when we look at an equation and the rate law excuse me, the rate law does not match the balanced chemical equation is because what the rate law matches is the slowest step in the overall process, what we call the rate determining step. There is always one step, one elementary step, one collision or interaction in a multi-step process that is slower than the other ones. And that slow step is what determines the rate law. So we're going to have two different possibilities here. And I think I'll go ahead and give these their own video here, just so this doesn't turn into a 30-minute video. So we're going to pick up next time talking about the two possibilities that we have when we're looking at a reaction mechanism. We can have the first step, because we're going to keep it simple. We're going to only consider a two-step process. So we could either have the first step be slow, or we could have the second step be the slow one. And so we'll take a look at both of those two possibilities. So I'll see you in the next